As we saw in the last lesson, we can use a digitally controlled resistor ladder to send a simulated analog voltage. There are a number of ways to convert an analog signal into a digital signal, and using a long chain of resistors is the simplest and in some ways the bestest way. By building a large string of resistors into a voltage divider across the power supply, and then using op amps as comparators, each comparator has a slightly higher reference voltage than the last. We now take our input signal voltage, the analog voltage we want to actually measure and convert to a digital number, and apply it to the non-inverting inputs of all the comparators. As the input voltage increases, each reference voltage it surpasses triggers the associated comparator. Each comparator represents a digital number on a single output, which we can run through what we call a priority encoder. Priority encoders have multiple inputs and set a binary output according to the most significant input, which is set high. You could do this with logic gates, for example. The advantage of this type of analog to digital conversion is it's fast, really fast. The only real time involved is the time it takes for the signal to propagate through the transistors and the comparators and logic gates, virtually instantaneous. The disadvantage is, look at the sheer volume of electronics involved. If it was an 8-bit converter, you'd have to have all of these comparators and gates for 256 inputs. A 16-bit ADD converter would need 65,535 comparators and their associated logic gates. The circuit size would be enormous and the expense very large. So there are other ways the electronics engineers typically tackle the A to D problem. By using a comparator, a digital to analog converter, and a counter. So basically the counter, driven by the clock, counts up in binary. The output of the binary counter is connected to the binary input of the D to A converter, so the output voltage of the D to A converter progressively climbs. Once the output voltage from the D to A converter matches the signal input voltage on the comparator, the output of the comparator goes low, triggering the counter to stop. The number on the counter output is our binary number, which represents the analog input voltage. Another signal resets the counter and starts the count over again to grab another sample. The advantage is this takes way fewer parts than the previous converter, but it's slow. It's driven by the clock, so for 8 bits, it might take as many as 256 clock cycles before it finally matches the input signal voltage. Now, if you're performing a 16-bit resolution, that could be as many as 65,535 clock cycles. So engineers devised a technique that was sort of a compromise. They used the same binary counter and D to A system with a comparator, but added a control circuit to control the count. Now let's say that the input signal voltage matched the digital value of 74. We now go through the process of arriving at that binary number. Instead of starting the count at 0 and counting its way up, the counter control circuit starts by setting the most significant bit on the count high. This starts the count at decimal 128. Immediately the comparator will output either a high or a low, depending on whether or not the input voltage is higher or lower than this midpoint voltage now being produced by the D to A converter. In this particular example, the input signal voltage is lower than the voltage generated by the D to A converter. So the comparator sends a low to the control circuit. Now the control circuit now knows that the input signal voltage has a value that is less than 128. It thus turns bit 8 low and sets the next lower bit high, bit 7, which has a value of 64. The input signal is higher than 64, so the comparator is now triggered high, and the control circuit leaves that bit high. We now know that whatever number it is we're looking for, it's higher than the value of 64. The control circuit now sets the next lower bit high, bit 6, which has a value of 32. Bits 6 and 7 have a combined total value of 96. The output voltage from the D to A converter will be higher than the input signal voltage, so the comparator sends a low to the control circuit. We now know that the number we're trying to find is less than 96. So the control circuit continues its hunt for the mystery number by clearing bit 6 and setting the next lower bit, bit 5, high. With bit 7 and bit 5 set, we have a binary value of 16 plus 64 equals 80. This is a higher voltage coming out of the D to A converter than the input signal voltage, so the comparator will send a low again to the control circuit. The control circuit now knows that the mystery number is less than 80. The control circuit continues its hunt for the mystery number by clearing bit 5 and setting bit 4, which has a value of 8. With bit 4 and bit 7 high, the counter has a value of 72. The D to A converter sends out a voltage that is now lower than the input signal voltage, so the comparator goes high, and the control circuit now knows that the mystery number is higher than 72. The control circuit now just triggers the counter to start counting up from binary value 72 and stops when the comparator goes low. This will happen when the counter hits 74. So instead of counting up from 0 to 74 and taking 74 clock cycles to arrive at the mystery number, by using successive approximation, we arrived at the mystery number in 7 clock cycles. Now, way faster, but it still takes time. The advantage being a small circuit and a small amount of time to complete the analog to digital conversion. By adding a register to the output, triggered by the control circuit to store that mystery number when it finally finds it, the register can hold that number to be accessed by the microprocessor while the converter performs its next successive approximation. So the number will sit in the register with a digital line set high, knowing that the conversion has been completed, and a number is sitting in the register for, whenever the microprocessor has time to come and fetch the number. Now, you remember how our digital to analog converter could use a resistor ladder to generate a voltage. If we change the output voltage of the digital outputs, then the analog voltage produced on the output also changes accordingly. The PIC microcontrollers, as well as your Arduino, have an onboard analog to digital conversion using the successive approximation method. On the PIC, you can actually set the voltage range detected by the ADD converter module. And this is, of course, set by changing the reference voltage produced by the D to A converter in the successive approximation circuitry. Now, you probably guessed that that voltage is set using registers. And it is only one of the settings you control using the setup registers for the A to D converter. Now, what I want you to take away from this lesson is that analog to digital conversion, because of the process used, it takes time. It consumes clock cycles in the process. So it does not matter whether your clock is running fast or slow, it consumes clock cycles in the process. And that time can vary. It might hit the mystery number right on its first try. So it might only take, 2 clock cycles. Or it might take up to a dozen clock cycles. But it takes time. So we access the control circuit in the A to D converter and basically tell it to start its conversion by setting a single bit, the go bit. The control circuit will clear that bit when it has finished its conversion and the mystery number is sitting in the register, the output buffer, waiting for you to access it.